I'm excited to introduce Andrew. I was trying to think back, like I don't even remember. I'm gonna have to ask him if he remembers the first time we've met. It's been a very long time. It's really cool when somebody has, as an organizer, you want to have a broad representation. You want to have academic perspectives. You want to have commercial perspectives. You want to have government perspectives. You want to have all these different experiences. Both, you want to have technical breadth, and you want to have like sort of domain or vertical or whatever you want to call it kind of breadth. And it's super rare that you get somebody who has all that in one person. And that's really what Andrew kind of brings. And so it's super cool that he has been a published researcher, and he has been developed commercial reverse engineering tooling, or commercial reverse engineering for commercial purposes for government. He's done all of these things, and so he's also one of the more thoughtful persons that I know. The reason we asked him is because every time I kind of hang out with him, I learn something new, and so I hope you guys do as well this morning. Please welcome Andrew Ruef.
Good morning, everyone. Thank you, Jordan. So when Jordan asked me to do this talk, I struggled to think of what to talk about. I sat down with a bunch of handwritten notes, which are now lost in the bottom of a lake somewhere in Maine, and I thought, what am I going to do? Oh, maybe I'll talk about what the last 20 years of reverse engineering tools have done. That would seem fitting. Thinking about the last 20 years made me just kind of sad because I had to confront the fact that I'm old. So I'll begin with a brief joke that I thought of during this time, which is if you see the phrase EIP equals 4141, 4141, and get excited, I'm here to remind you that it's probably time to schedule your colonoscopy. So with that brief reminder of our mortality aside, let's talk about the agenda for this morning. So I'm going to sort of try to hit through 4 different things that I've thought of. I'm going to start with a view of the world and reverse engineering problems. We're going to take a brief detour into talking about the process of science. I'm going to pontificate a little on sort of what makes a good reverse engineering tool. And then I'm going to try to wrap it all up by thinking about what I'd do if I had my youth again, which is a great thing for people my age to think about, especially today. But first, what is a tool in the human sense of tool using? So my wife knows a lot more about this. She has a PhD in neuroscience, an actual science as opposed to computer science, which is what my PhD is in. So the interesting thing is that the way that our brains evolved apparently over time, I'm not the expert, she is, she's explained this to me. When you are using a tool like a knife or a hammer, you're holding something, or you're using something, you're piloting a vehicle, you're driving your car, things are happening inside of your motor cortex to change the way that you're perceiving the world, to incorporate the boundaries of the tool that you're using into the way that you think of how your body is interacting with the world. And this is kind of what gives us our edge as a species and let us dominate the planet, probably, because it means that we can pick something up and we're like, no, this isn't a stick, this is me now, and I'm using this to do something. And you find this, right, when you're interacting with things and you're describing how your day went to someone, when you're like, oh, this person was really close to me when I was driving, they were on my ass when I was driving to work. They weren't actually, right? They were 15 feet behind you, in a different car. But because you were using the car as a tool, things that are close to the car feel close to your body as a person. When you're using your knife and fork to eat breakfast 15 minutes ago, you're not thinking about I'm holding the fork and then that's spearing the food and I'm putting it into my own mouth. You're thinking, oh, I'm doing this, right? Because the tool is a part of you. So the tools have become an extension of your experience when you're using them for everything else. So does this carry forward to computer-based tools? And I think this is sort of obvious, right? We're oh, we use all of these things to mediate our experience with the world, and you can see this when you talk to people about them doing work through the day. They're like, oh, I looked at the binary. It's no, you didn't. You used an instruction decoder to generate a sequence of text, and then you read the text. But there's a lot of mediation in between sort of the raw data and what you were doing. That might seem like pedantry, but I think it's an important distinction because you're trying to think about, well, if I'm using tools in the real world, would I want a fork that is steam powered with artificial intelligence. This joke also doesn't age super well because I think today people do want forks with artificial intelligence. But what I want the steam-powered AI-driven fork to automatically like shovel food into my mouth, like no, I want to be the one that does that. I want to be able to use a thing that lets me do something that my body doesn't already do, but in this like mediated way where it's an extension of my own experience. So what are these tools doing that like think for you that you want, and then what aren't? And I was thinking about this a bunch, especially because of artificial intelligence, because in my mind, I think the forefront, or what you want to do as a tool author and someone that does tool research, especially in something like reverse engineering, is people like you are doing problem solving, creative problem solving, and quantitative reasoning, and we want to support that as an activity. And the tool is essentially like a fork for a creative problem solver that's approaching the problem of doing reverse engineering as in eating a meal. You aren't trying to solve the whole problem for them. You're trying to give them utensils for their brain to digest the problem. I just came up with that metaphor now. You can applause. So why, when you're looking at addressing this, you also have some questions that seem very fundamental, but I think are also a little worthwhile to noodle through. So who uses your tool and why? What problems are they trying to solve? And have you solved those problems for yourself as well? That might seem obvious, but I myself have answered sort of I don't know to all of these questions at some point in my life. So either I'm particularly stupid, or these are kind of worth thinking about, and maybe answering them or thinking about them intentionally will help you as well. So when you're also thinking about, hey, how do I make tools for someone else, maybe what I want to do is think about how do they already approach the world and experience it, and how can what I give them help them interact with the world? How do I give them information that they can understand? What are they already comfortable with? What are they already doing? So from a like tool creator point of view, I started here, and I was like, okay, how does this intersect with reverse engineering? This is a small hobby horse of mine when it comes to doing quote-unquote binary analysis. So frequently you'll read in literature, especially earlier literature, someone will say, oh, we have this binary analysis tool, and we'll perform, it does what it says. You put a binary in, it takes facts out. And you'll discover when they get to things like function analysis, they'll have very particular theories about, well, this is how parameters are passed, and these are how local variables are stored. And they say if something doesn't do this, it's because the binary is obfuscated, and we don't deal with obfuscation. You should run that as like a pre-step and then analyze the deobfuscated binary. And I realized at some point, well, wait a minute, so many assumptions that we make about quote-unquote binaries are really, is it the output of GCC or MSVC? So I came up with this increasing scale of weirdness, where there's basically a difference between what is the output of GCC and what is an acceptable sequence of instructions according to the x86 ISA. And those are different things. Because you can do stuff like, oh, I'll have a custom obfuscating compiler, or I'll hand jam some stuff in an assembler or a hex editor that will technically run inside of the processor, but if a tool like IDA tries to digest it, it won't really work. And those are, weird, but then you have things that people are used to doing, like, hey, C code written by the least interesting person in the world, or this also known as the Spec 2006 benchmark. And then large normative applications like Linux kernel, slightly less normative applications. When I originally made this diagram, Internet Explorer actually existed, which is also making me feel old. Anyway, I think that when you're thinking about making a tool and you say, hey, this is a tool for binary analysis, one important question that you can ask yourself, going back to the previous example of who is using my tool and why, is perhaps people are doing compiler output analysis in that they're saying, hey, the programs that I'm analyzing were written in C. They did come from MSVC or GCC. I just don't happen to have the source code. So that's OK that I make all of these assumptions about the structure of these programs, as long as they're sort of upfront. Because someday down the road, someone is going to have a program written in Go or Rust. They're going to try to analyze it using my quote-unquote binary analysis tool, because binaries are binaries, right? But they aren't. Some are compiler output from a language that you know, and some are compiler output from a language you don't know, and some have been like custom hand-jammed. So it is probably important for you to have, at least in your mind as a tool user and a tool developer, what are my implicit assumptions about the provenance of the things that I'm analyzing? So the other question is, when we're talking about, hey, this is compiler output analysis, is every compiler a C compiler? And the answer is no. When I originally started, when Jordan asked me to give this talk, I sat down and I thought, well, wait a minute, what was hard 20 years ago? And a hard day was when someone brought you a compiled C++ or Delphi program. And I thought, well, at least we don't have to deal with Delphi anymore because no one really writes that. But still, compiled C++ programs are hard. But the task of analyzing Delphi programs didn't get easier because our tools advanced. It got easier because people stopped writing them, and then we didn't need to analyze them anymore. But in their place, compiled languages like Rust and Go actually, and Swift, sort of achieved more mainstream status, and you will see those day to day. You probably won't see OCaml binaries day to day unless you're playing a particularly mean-spirited and/or French CTF. But they're out there. And the fun thing about analyzing OCaml programs is that when you sort of like release your vision from tunneling in on like C programs compiled by GCC, you'll realize that people sort of looked at the x86 ISA and thought they could do some truly wild and wonderful things with it. So for example, OCaml, when it compiles, is sort of both a language, you control the input language. And so the input language, so you might think, well, in C, you can have pointers that point to anything. So you're basically just programming an assembler with templates because the input language, you can do so much, so then the output and the input are kind of closely correlated. But in OCaml, and programming languages like it, your use of references is very tightly scripted by the type system in the programming language. So you can't just like manifest pointers to arbitrary objects anywhere. And that makes programming in it easier, but it also means that compiling it is easier because you can do things like, hey, I'll implement a full mark and sweep garbage collector if the entire address space is only OCaml code. No problem. The garbage collector can run through. But wait a minute, what would make life easier for the garbage collector? All values that I spill out to the heap are going to be tagged based on type. So I can know conclusively whether or not some word-aligned value inside of memory is a pointer or an integer. And how do I do that? I'll tag the low bit. If the low bit is 0, the value is an integer. Sorry, the value is a pointer. If it is 1, the value is an integer, and I shift it to the right once to make the actual integer value. So this means that when you're analyzing the code, there will be all of these like weird shifts on different values, and you're like, what is that? And unless you know that upfront that the input was OCaml, and you know how it represents those values inside of the runtime, your analysis is going to be a little bit at a loss. This also means that when we approach the world from the point of view of binary analysis as saying, oh, I have an assembly program and I want to decompile it back up into C, what if the original input wasn't C? That is going to look really weird, especially if you start with something like Go and move backwards. So from a binary analysis point of view, you have to think, oh, all of these programming languages get to make a lot of free choices about runtime and the way that their code compiles. I have to factor that in when I'm thinking about doing binary analysis. Haskell, for example, is a very interesting programming language to look at when it's compiled to native code because they don't make a lot of assumptions about what is inside of your stack frame. I think the last time I looked at Haskell, which fortunately was like 8 or 9 years ago, there kind of weren't that many assumptions about stack frames, and individual blocks of code would reach very far, and IDA would get very confused. What this means from a meta point of view, if you're thinking about, hey, what do I put into my reverse engineering toolbox, and how do I analyze the world, is our dynamic as reverse engineers and reverse engineering tool creators is fundamentally reactive. We don't actually make the thing. We analyze the thing that someone else made. So we're kind of perpetually waiting for someone else to make the thing, and then we'll go and figure it out. So sometimes I and other people like me have been tempted to try to create a sort of unified theory of everything, where we'll say, hey, we can analyze anything we want as long as we put it inside of this sort of like box or general area, and then everything will relate to itself. We'll have one grand unified intermediate language for all analysis, and it won't matter if the program is an amalgamation of like Java and C and Go and C++ that's all calling to itself inside of the same address space. It'll be okay. It'll all be in the same intermediate language. And this will work until someone invents Zig. And then you're like, oh, how do I put that in there? Or until it sort of achieves popularity. This also means that you have dynamics like, hey, is this a cutting-edge language feature or an obfuscating compiler. And that kind of depends on what decade you're looking at something in. There was an episode, I think, many, many years ago where a popular antivirus company went onto the internet and they said, hey, we've discovered this sophisticated malware which is using a custom programming language of some kind because the parameter passing is like nothing we've ever seen. And it took a few months on a mailing list for someone to point out, no, that's what MSVC does when you turn on this particular like optimizing mode, which is actually a default one when you're doing a production compile. And the compiler has determined that a particular method is entirely internal, and it can pass parameters to the method in whatever way it wants. So it was using different registers to pass parameters instead of spilling everything onto the stack. And this antivirus company had thought, oh, this is something that is very abnormal, when it was probably something very normal, something they just never seen before. So you're always reacting. And I think that is kind of a disadvantage that we have when we're thinking about how to be strategic in terms of tool planning and like what tools to create. As an aside, I kind of am a little like worried because as far as I know, if you have the task today of reverse engineering binary Go or Rust code, my apologies, because as far as I can tell, that is basically 21st century Delphi. We don't really have good tools for this right now, so you're going to struggle bust some. I don't know if anyone is working on it, and I think part of that, which I'll get to later, is blunted by the fact that a lot of the Go or Rust code that you would want to analyze is open source anyway. So why reverse engineer it when you can just go to the GitHub URL for it and download it? Also, as an aside, I remember being profoundly angry when I was in grad school because I'd spent the first 10 years of my life looking exclusively at x86 assembly code. And there were all of these papers that got published about doing binary analysis on JVM programs. And this was very confusing to me, mostly because I'd never actually looked at either Java source code or Java binary code. And so I had no idea what a Java binary truly was until I had to do a project in Java, and my advisor said, oh, go and read the JVM specification and figure out how the class loader infrastructure works. And so I did, and I discovered, I was prepared for it to take a few weeks, but I discovered I read the whole specification in about an afternoon because there's only like 20 instructions in the bytecode language. And I got really mad because I was like, oh, all these problems that you have in assembly code of you can just like access arbitrary indexes into memory, and you can like have the stack sort of be anywhere, and all these instructions make these implicit accesses into memory, which is just this arbitrary untyped array. Those are all gone, and you actually have an intense amount of structure in this quote-unquote binary program when you're looking at JVM bytecode. I was actually pretty mad because all these people were saying, oh, we've done this binary analysis on Java code, and I'm like, sure, there are like not as many types as there were when you had the source code, but it's nowhere near what a machine code binary is. So I think that working in that paradigm is easier, and I was then a lot more comfortable with something like, oh, what could we do for like compiled C# programs or other Java programs? But I don't think we can do the same thing if we're thinking about Go and Rust, but I think that is okay because you can think, oh, is there something specific now that I've fixated on or fixed on? I am doing compiler output analysis because the original compiler was the Go compiler. So what did it do that I can exploit when I'm reverse engineering and going back? So I mentioned graduate school. So sometimes I think to myself, well, where do ideas or new ideas in this space come from? And when I was thinking about that, I was like, well, what if we flip it a little bit and ask, not necessarily where do the new ideas come from, but how are the new ideas rewarded? And so what would motivate someone to come up with a new idea? So this is a little bit like, hey, if I'm sitting in the audience right now and I'm thinking, how do I choose what to work on? You kind of have 3 different things that I can think of for getting rewarded for having a new idea. So one of them is being able to publish at a conference like this one and speak to a bunch of your peers and say, hey, here's this cool thing I did. That feels pretty good. If you've never done it before, I strongly recommend it. It's very neat. It also gets your idea out there in a way that is very difficult to do otherwise. People pay attention to conference proceedings. People pay attention to talks. They'll watch the talks while they're sitting at their desk eating lunch. And then maybe they'll like have an inspiration from it. They'll cite you in a talk or formally later, and then they'll like, you have now contributed to the great shambling forward march of science and human civilization. Congratulations. You could also skip a few steps and release a tool. You could just go onto GitHub and say, yep, here it is, here's the code. And either you sort of dump it and run, or you can soldier on for a few years and make contributions and potentially try to get a small community of people that are also like contributing to your code and your tool. Or you can keep all of it to yourself and use your idea to do something as, for example, a commercial service that no one else can. And then you're just sort of this like mysterious force that's capable of like analyzing binaries at speed that no one can really comprehend because you have this like edge in your back pocket. And I think if you're thinking about how do I like take my idea and make something of myself from it, these are kind of the three things that I thought of. And where does this come from? You know, you could go to work for a company, you can go to work for a university, or you can just kind of live on your own. And I think an interesting thing about reverse engineering specifically, if you're thinking about it as an engineering and science discipline, is that we don't need large labs with $100,000 machines as table stakes, nor like a $20,000 a month budget for like reactants and agents. You just kind of need to pay your rent and have a computer, a very modest one, and sit there and plink away for a few years. So you need time. And time and money at that scale can be pretty cheap. That's at the first order. But what you really need, in my opinion, is a real problem that matters to other people that you will be rewarded for, back to the previous slide, that you can make progress on, and perpetual connection to it. I'll get to that. So what you really need to do is find a buddy. Find someone who's trying to like, which could be yourself, but ideally is someone else, who has a particular goal in mind where they're like, hey, yeah, I just got this tiny mountain of like C# middleware applications and I need to get through analyzing all of them. But there's just so much. What do I do? And then you show up and you're like, oh yeah, I'll like help you make tools, but what kind of problems do you have? I'll help you answer them. And then that collaboration will keep you as a researcher and tool developer on track to create real answers to real problems instead of potentially getting sidetracked and thinking, oh, I know what I need to do is implement these 5 different pointer analyses that I found in this one paper from 1988, but there's no source code. This will be an interesting way to occupy my time for the next 6 months. It will be an interesting way, but no one will care. As another aside to the aside, in general, a problem-solving philosophy that I've tried to cultivate in myself, and also usually failed at, but sometimes succeeded, is try something, but adapt as quickly as you can to feedback from objective reality. So this can include feedback like, hey, I think that all functions that are called, back to the antivirus company example, will store variables and parameters in this way. But as soon as you find a counterexample, you should start to think very curiously and seriously about why, if it's a larger trend, if it's some one-off thing that someone hand-jammed in a hex editor, or if this does represent a true counterexample to something that you were thinking of as an axiomatic way that computer programs worked. And if it is that counterexample, you need to think about what that means for the precious theory that you've been cultivating in your head. Likewise, if you go and you take something and you show it to one person, and they're like, I don't like that. Like, I don't want to do this. I don't want to click all these buttons. I don't want to have to write Lua that plugs into this thing. I want to do this other. But you don't hear that other thing because you're like the fool. If only they understood. You should probably have listened to what they said when they were like, I wanted to do this other thing, because that moment was gold. I've passed up many golden moments like that myself. But in general, if you get feedback from people on like, I don't like that thing, I want this other thing instead, you should probably listen to it and incorporate it. You don't need to take it at face value or completely like as is. You just need to take it as a signal from someone that would potentially be a consumer of your ideas, that they didn't like that and they had this particular thing in response. You don't need to do exactly what they said in response, but you need to try to think about, well, why did they say that? Where is that coming from in reaction to the vector that I proposed? And what do I do with that? So the other, when I was thinking about this, I was thinking about in the past, what tools have I used that I do like? So in graduate school, a slight detour away from reverse engineering, but still in the area of software security, we ran this project called Build It, Break It, which was a combination computer programming challenge and vulnerability identification challenge. The normal capture the flag dynamic is the organizers spend a year or so putting together a collection of exquisite puzzle boxes, and then they give them to the contestants to study and solve over the course of a weekend. This is fine. I always rebelled against this a little bit because I thought that the construction of puzzle boxes, though enjoyable, was a little artificial, even though frequently many organizers are basing their puzzles off of problems that they've encountered in the course of their real work. So I thought, well, what if instead we ask people to first, in one weekend, do a programming competition, and then the second weekend, we take the output from the programming competition in terms of like, hey, this is a program that implements a client-server application, which is an ATM in a bank. We have dozens of those because dozens of people tried to solve that as a programming challenge. And then we give it to everyone else and say, hey, try to find vulnerabilities in this client-server application that's an ATM in a bank. This was interesting because the vulnerabilities that you were trying to find were live. No one intentionally placed them there. There weren't really any cute tricks. No one could tell you what the answer was. If someone came to you and they're like, hey, what is the vulnerability in submission number 19? I could say, I don't know. That's your job. Like, there might not be. There probably is, because a group of 3 teenagers wrote it in 24 hours last Saturday. So if they did it without introducing any vulnerabilities, I will hire them. But there's probably something there. You should go look. And we noticed that there was a trend where teams that used advanced programming languages, such as Haskell, would do very well. And this comported in the programming languages lab with a bunch of our prejudices about the world, because we thought, well, obviously these sophisticated programming languages are the way and the light, and you should just use them. But in the back of our minds was this concern that perhaps it wasn't the case that the sophistication of the programming language meant that the output was good, but that the sophistication of the programming language has gatekept the people that could use it. And those smart people that were smart enough to use Haskell would do just as well if they wrote in Python, because they would be that smart but working in a programming language that didn't have the same advanced type systems. I'm told this is a very similar hiring strategy that Facebook used, where they were like, yeah, we'll get all these ML hackers. They'll spend years in like undergrad and grad school programming in like SML at CMU, and then we'll have them come on down and write PHP. And it'll be okay because they've like been trained into good discipline with a strong type system, and now they'll write like PHP for us, which is a fun trick. When you think about tools that you like, I also try to expand this out to programming languages, and just sort of any kind of computer-mediated tool that you use, TCP dump, Wireshark, et cetera. Like, what is it about these tools that I like? What is it that I've sort of ingrained into the way that I like use computers to mediate my experience with like other humans and other computers? But then also, my other example is, can you think inside the box along with what this computer tool is doing? And here, I will turn to bag on Ghidra for a little bit. I was using Ghidra to analyze some binary, I forget what, and I had the listings view on one side and the decompiler view on the other side, and there was a function, and I wanted the cross-references to the function. And because I grew up using IDA, X is basically a muscle memory for me, which I always use on any tool, and I'm always disappointed when it doesn't work, even though it's been decades. So I right-click on this function in the decompiler view, and I select show cross-references, and I get like one thing. And I'm like, that's not right. This function is like the central access checking mechanism in the thing that I'm looking at. I know it's called in dozens of other places. I've seen it. And after like 20 or 30 minutes of noodling over this in my head, I have the presence of mind to do the same thing, but in the decompiler listing, not the decompiler, the instruction listing. I find where the function call is in the assembly, I right-click it, and I get like 24 cross-references. And it's then that I realized that the data model that the disassembly has is somehow in the back end different from the data model that the decompiler has. So when I'm asking for cross-references of symbols between these two different views, I'm getting two different answers, and the tool is not like being malicious or trying to like get one over on me, although maybe it is. It's like giving me what it knows from the two different vantage points that it has for this particular task. So if I had that as a concept of how the tool worked, I wouldn't have been surprised, but I didn't, so I was. So when you're thinking about these tools, there is an amount of, hey, the tool is doing something that I could do, but faster, and I understand what that is, so this partnership is natural. It's like the fork. I understand what the fork is doing. But when that starts to escape from you, you're like, oh, I don't understand what it's doing, and it's confusing me, and it doesn't matter that it's doing it faster than me because I can't appreciate it or anticipate it. From here, I want to go over to ask, why do people actually perform the task of reverse engineering? And I think asking this question goes back to an earlier motivating question that tries to tell you, hey, where should I go with these particular tasks? And what type of work am I supporting? And I think this is broken down into a few different areas. I'm curious if I missed something. Someone can find me later and tell me, oh, you forgot about this, and I would be genuinely curious. But when I was thinking about it, I thought, okay, well, basically, I used to think that the task of source code recovery was somewhere between like a false story and a joke. Someone would say, oh, I lost the source code to this particular thing. It's like saying I lost the keys to this fancy BMW. Can you help me like get into it? But I have discovered multiple people for whom this is a real problem. One of my favorite examples was there was an observatory out in California where there's like this 20-ton at least telescope, big observatory, like motorized shutter doors that open and close, the telescope like wheels around. And there's software that controls like the track and the motors and the shutters and the whole thing. And what else? That software is written to support Solaris, because obviously at the time, sun was going to be around forever. And the contract that the observatory ran didn't require the contractor to provide the source code. Not that that would have helped much today. So there are all of these like binary Solaris kernel mode drivers that are chilling out on these ancient Spark stations in this observatory in the hills outside of San Francisco. That no one, like if there ever was a new feature that they needed to add or they needed to change some parameter because they needed to update some part of the system, they're kind of screwed. They need reverse engineering to do source code recovery to figure out like where all the changes need to be made in these drivers. I don't know. I was the first time I was like, wait a minute, this isn't a joke. You didn't like lose the source code to Windows. You need someone, okay, wow, neat. But then also things like, hey, I need to identify vulnerabilities and perform legitimate feature analysis. And then finally, malware analysis. So I think this is also interesting to think about because, honestly, if I also go back and think about 20 years ago, your desktop could be hacked by like drive-by browser exploitation that had 0 days against Firefox by people that wanted to install fake antivirus on your computer. Like you found out about the intrusion because this pop-up would show up that would be like, hey, your antivirus license has expired. And you'd be like, I didn't install antivirus. What's going on? And there would be this kernel mode rootkit that would conceal its presence from stuff in System32 entirely to try to like convince you to buy something you didn't need. It was a wild time. And those times are like completely behind us now. And so I think about this because there was a time, and a buddy of mine had this analogy where he said, hey, did you know that before the invention of the automobile, New York City had this big problem because everyone got around by horse. And the horse-drawn carriages, you would ride the horse. There were just horses all throughout downtown Manhattan. And the big problem of the day was horse poop. The horses had to poop. They just sort of pooped in the street. And dealing with the poop was a big problem. You could make a lot of money by going out with a cart and just like, well, not a lot of money, but like you would make a living by going out with a cart and collecting the horse poop and moving it away. But people were like, wait a minute, here's the population. The population needs to be supported by a certain number of horses. If the population keeps increasing, the horse population will keep increasing, which means the horse poop amount keeps increasing. And eventually, Lower Manhattan is going to be nothing but horse poop. It's just going to be like 2 meters of horse poop everywhere. There's no way that we can support the infrastructure required to like remove all the poop. What's going to happen? What happened was the automobile. Now there are no horses in Lower Manhattan. Well, effectively no horses in Lower Manhattan. So we thought about this when we were thinking about malware, because it used to be that it was very possible to just have like tons and tons and you could have like 2 or 3 different botnets on one like Windows computer, and your problem as an incident response shop was just being inundated with the amount of malware that you had to reverse engineer and deliver insights on. And it has been a little bit since I've been in a like true blue defensive security company, but it really seems like that trend is more on a downswing. Like sea changes in the way that computer security stuff works have a downstream effect on the volume of reverse engineering tasks that you need to perform. So I was thinking about that when Jordan asked, hey, what do you want to talk about? And I said, the last 20 years, why not? So when you're talking about tools, you're also going to think about, well, how do I approach analyzing these tools? Like, how do I approach performing analysis tasks inside of different tools? And you have like a few different ways that you can approach this. You can take like a top-down approach or a bottom-up approach. I prefer a middle-out approach, unironically. I will sort functions in IDA by size, and then choose a large one. Not the largest one, because that is probably a parser, but like 2 or 3 down. Like, go there and just like look around, and that's probably some interesting driver logic, and then you can go from there to figure out where do things start from and how do things go. But then as you're driving around, you are renaming things, you are changing the structure of things, you're adding structure of things, and then as you learn new things, you go back and revise those decisions. And then if you're having a really good day, you're writing code that interacts with those, where you discover particular patterns or idioms, and you say, hey, I want to script like renaming stuff or adding structure. And all while doing this, you have a pretty good understanding of the internal model of the tool that's you're working with, either because you wrote it yourself, or you've read the source code to it, or you've just worked with it for so long that you like when IDA says return to, like that means something weird is going on here. Like, I should probably switch out of hexarrays and look at the disassembly. And there are pretty good tools that support this, and I think this is where tools like IDA and Binary Ninja come in, where you have this very easy not very easy, but over time you develop this understanding of how the tool is working. You can work incrementally with the tool, and add understanding and work incrementally. And unfortunately, what I don't know is a shortcut for acquiring that understanding besides just working with it a whole bunch. As another aside, one thing that I was thinking about was every time someone approaches the task of binary analysis that I've seen, they're like, oh, what I really want is I want to look at the source code. So can you give me something that like decompiles down to source code? And I had this as a thought experiment or counterfactual in my head of, well, okay, yeah, source code good, binary and like decompiler output bad. And why? All the names in the decompiler output are weird. It's all like func_1234 and v0, v1, v2, or whatever. But what if I take your like open source code that you're doing vulnerability research on, and I alpha convert everything so that the names are like decompiler names? Is reading that going to be easy? Is that going to be easier than reading the source code? Is it going to be easier than reading like the binary? I actually think that one of the things that, and I think this is sort of on the borderline of obvious, is what we really struggle for is good names for things and good context for things. So if you're reading code, you're going to go through this translation step in your head of like, oh, this is an index into an array. So being able to naturally snap in and say, yep, that is called IDX now, skips a step when you're reading the code. So really what the tool is about is taking your understanding and putting it down and like writing it and having it available for your reference as soon as you read it, instead of having to like understand, consciously interpret, and then move on. So this is the part where I stop and I say, well, if I had an opportunity to go back and work on different things, what would I work on today? And there are sort of 2 overall themes. One is this idea of simple tools versus complex tools, and then the other is I would sooner find a practitioner and buddy up with them. And I do also kind of think that some problems are just sort of mind traps. And maybe some of these are problems unique to me, but every time I came across some C integrated with some Java, I thought, well, this is really annoying because I have IDA over here and JADX over here, and I have to like translate between the 2 of them. Wouldn't it be neat if that was all inside of like one tool? And this is where I have a spray bottle next to my desk that I use on myself. It's like, no, you're overgeneralizing. You're going to have like 7 tools on your desktop. That's fine. You're going to flip between all of them, and it's going to suffer a little bit, but attempting to generalize it is going to be a lot of work that will not work ultimately. And then, yeah, when Zig is mainstream, you're going to need an 8th tool, and you need to figure out how to plug that thing in there too. So that, I think, trying to recognize like, hey, am I standing on the precipice of something that doesn't have a bottom and I could just sort of fall into, is a decent instinct to have as a researcher, and try to recognize where the stairs are to go down like one floor instead of just falling. The other thing is sort of like a universal approach to anything. Someone who's like, oh, I'm going to try to make a universal decompiler, or I'm going to try to make a universal deobfuscator. And it's like, yeah, I don't think that's going to work, both because that's really, really hard, and also because, especially in the sense of obfuscation, you're not really in the natural world. You're in this weird game of cat and also cat between people that are making obfuscators and deobfuscators. And it's a reactive dynamic where you'll produce this technique and then someone will intentionally target it. And now your like universal thing doesn't work anymore because someone figured out some flaw in your reasoning. So I would also go back and be like, hey, there are some ideas that are like just not worth chasing, like some of these. You should try to figure out something that you can make incremental progress on. So I also spend a lot of time thinking about this unironically because of artificial intelligence. People that are using your tool should understand what your tool is doing while it's doing it. If something is and that can be okay. So if your tool is like, hey, I'm gonna like pop up a whole bunch of windows and a lot of stuff is gonna happen, and you're gonna like walk away from the computer for like 5 or 10 minutes, but when you come back, you'll like have some answer. That is pretty okay. When I was in grad school, I did a short detour through Microsoft Research, and I worked in a lab with someone that did their entire career in compilers. And it was a bit of a culture clash in terms of algorithmic design, which is also a weird sentence, where they said every time I submitted a PR, they would be like, hey, can you come to my office and do an algorithmic complexity analysis of this algorithm? And I would be like, okay. And if it wasn't polynomial, they got really mad. And basically the first time this happened, not like really, they were like, no, this is unacceptable. You can't put this into a compiler. And I was like, I'm from a programming languages lab. We're happy when there is a decision procedure. Like it could be doubly exponential in runtime, but like it'll figure it out eventually. Like maybe you leave it running overnight. And they were like, no, programmers will not accept that. Like you have to, like the compiler has to terminate on some reasonable time frame. Joke's on them, Rust wasn't popular yet. They expect that like the compiler will run in like, a few seconds at most, and they'll get grumpy if it takes longer. This was a perspective that I like hadn't really seen as a programming language graduate student before, because we were used to taking like a few megabytes of text and throwing it into Z3 and then going off to the pub. But like, I accepted it because the programming languages community as research was different from like the compiler engineering community. I think that, and then also as an aside, this is around when people were working on Daphne. And Daphne had a similar culture where if you were Daphne is this formally verified programming language where on the front it looks like an imperative programming language, but you can put in fancy like pre and post conditions, and the compiler will use Z3 to prove whether or not those pre and post conditions hold for different functions that you write, and then you compose them all together into a program that has pre and post conditions. Very fancy. Under the covers, it's using Z3 inside the compiler toolchain. They didn't have this only polynomial algorithms business. But as a user, if you didn't understand like what Z3 was doing, it's kind of impossible to understand what Z3 is doing. But if you didn't even know that it was there, you would be like, hey, I wrote some code. It seemed to check out for me. Press the compile button. It's still thinking. How much longer is it going to think is, I think, the question that your user is going to have in their mind. If they can answer that question for themselves, they'll put up with the time. But if they don't, they'll be like, maybe it's just gone out to lunch. I should Control-C this and like try something else. The Daphne people were a little bit, they didn't really know what to do with this point of view of the world, because they were like, yeah, we also are programming language researchers, so we're used to things taking a long amount of time, and we write the tool. So if something is taking a long time, we'll like add some print statements into the compiler and then recompile the compiler and then recompile the program we're trying to analyze, and we'll like learn more about what's going on with these with the different proof terms and what proof term is like choking Z3 out. And you're like, yeah, other people can't do that, so this isn't an appropriate like tool using situation. But people should be able to understand what's going on inside the tool, and what you should be doing is helping with the creativity and quantitative reasoning that's like already occurring. You shouldn't be trying to like preempt or circumvent that. This does have a sort of unfortunate side effect, which is it can be a little elitist. You start to say, hey, I'm not making a tool to like take someone who is okay and making them like inherently more skilled. You're like, if you have skills, I'm going to like make life easier for you. And if you don't, you should probably get those skills in tandem with like figuring out how to use these tools, but these things are not going to really like work together that well. This is uncomfortable, but I've sort of come to accept it as inevitable, which is kind of a saying for 2025. And then continue to like be an extension of what the body is interacting with the computer. And then finally, go out and find a buddy. Find someone that is doing work like this, that has a genuine task, that has they need to answer the mail on something. Find a tool that they already use. Add a button to that tool. Ask them to press the button and then see what happens. This can be a kind of fun loop to get into. Sometimes, earlier in my career, it was kind of unfortunate because someone was like, oh, hey, we've got like all of these different things, like 2,000 or 3,000 locations where this pattern might be a true positive or a false positive. Do you think we could write a tool that would like narrow it down? I said, sure. It took me a few months. When I came back, they were like, oh, we just looked at all of them. Okay, neat. Glad I did that. Did we ever wind up using that? No, because they looked at all of them. But if you can get things inside of that loop, and also this is one of those occasions where you can try to recognize and predict the drop. So you can say, hey, yeah, I can write this tool, but not in a time frame underneath where you can probably obviate it by just like working really hard. So we'll just work really hard, and I'm gonna go do something else. But yeah, I think in general, when you approach someone who's already doing something and you say, hey, I'm not gonna like give you a new tool as a lifestyle, but I am going to like give you a new button that will do something that you can anticipate what happens when you press it. And then maybe it'll crash, but probably it'll like give you some answers, and then we work together and refine what it does. They'll be a lot more receptive to working with you than you might think. So then I also was thinking, what gaps, and I promise this is near the end, are exciting to me right now in terms of tool development and reverse engineering. And honestly, I struggled a little bit to think of what reverse engineering tools, what tool challenges were challenging, because I've accepted so many things as intractable, which is maybe also a sign of age. But one thing that I think we've never really cracked and would be really worthwhile to crack is a longitudinal understanding of programs. So sometimes you're like, hey, understanding this particular thing is going to be an evergreen question. I'm going to learn things about it, but they're going to update it. And then I need to understand what those updates mean in context. It would have been great to have that. The best time to start a longitudinal program analysis task was 10 years ago. The second best time is now, I guess. Having something that worked on that would be pretty neat. I think that's something I would work on now if I was capable of working on something. And then the other thing, which is completely different from all of this, although it just blows my mind that we're at this particular point, is understanding IAM and access control implementations. As an aside, early computer security research focused a whole lot on like labeling objects and studying the relationships by permissions between subjects and objects. And if you look in the literature, all of that research kind of like peaked and then ended between like 1999 and 2002. People were like, hey, we figured out how to make Unix permissions work. We figured out how to make like Windows ACLs work. We transitioned all of this work into industry. It's in the operating system now. We're done here. But they weren't done here, because then every application at every further abstraction layer up the stack needed to reinvent permission management. And then also it started to go down the stack as well, because cloud needed to do this too. But most of the researchers have kind of checked out. They're like, no, we have like permission models, and there are these papers about like ACLs from the 90s. They nailed it, all is well, don't worry about it. And then people try to make like different fits and starts of doing this in open source. So Amazon has this Cedar thing, but then they kind of walked away from it. and there are a few other attempts, but getting them like applied writ large to like complicated stacks, especially in the cloud and across application space, haven't really panned out. So you're currently at the point where you log into the AWS console and it's like, yeah, you've got 3,000 different IAM tags. Do you know what all of them mean? No, no one does in total. Good luck. Hope you figure this out and don't shoot yourself in the foot. I find that like mind-boggling. I think that is a very interesting gap to like understanding the world is understanding inside the context of both different applications as well as like cloud computing stacks. What do all these different permissions mean? Anywho, this little red ticky thing in my bottom right vision says 1 minute and 35 seconds, so I think that's a decent time to call it so I can drink some of my coffee. Thank you very much for listening to Old Man Yelling at Cloud. Thank you, Jordan, for having me here. Have a good Saturday.
Oh, thank you so much.
Ooh, a box.
Yes, you get a little, excuse me, you get a little special box.
Ooh.
Just we want to thank our keynotes. That
Have they seen the box? Have they seen the contents of the box?
Yeah,
yet?
you can show.
Look, it looks like that.
Yeah.
Yeah.
So thank. We really appreciate it. Did that count as thoughtful? I think that that absolutely counts thoughtful. So questions. Let's get some more things out of it. We got time. This doesn't count for questions. So we
This doesn't?
Yeah.
Yeah. Please questions.
So we'll run out. And are there any questions?
You can ask a question about anything. Yeah.
Test. Hey, I'm sorry I asked a question yesterday at the first speaking event, and I think it's very similar on your talk in the beginning. And in the very first few slides, it's a problem I've worked with currently, kind of bridging the gap between Red Lattice and the Department of Defense. And you talked about, with everyone here talking about defining the problem and then reasoning, and you kind of translate it. You talked about the quantitative, with which everyone in this room is very familiar with, but I thought the second, third, and fourth slides, the way you described it was the qualitative. And those people, like in the Department of Defense, define what the problem is for us. And some of us have an idea of how to fix that problem. And I think I wanted to reiterate, and what role, even though you didn't mention qualitative in there, what role do you think that we need to look at in the qualitative aspect to show our customers or who we're trying to problem solve with? How does that role come in translating how our tool is going to help them fix their problem?
Yeah. I think that if you also want to talk about proactive versus reactive, large government institutions are also kind of fundamentally reactive, I think, or at least in my experience. So one benefit is as an individual or an outside institution, you can propose a methodology or a tool, and you can say, hey, look at this. Like if you click this thing here, this thing happens. Or, hey, we have this algorithm or this approach to doing data analysis. These are the results that we get. Large institutions, I think, frequently value the perspective of the outsider more than the insider. So you can see this in like corporate behavior where they would rather acquire something than have an internal team like propose it and then build it on their own time, even if the result would be more advantageous to the institution if it was insourced rather than outsourced. I think that is generally pretty true. The downside is that though they are more receptive to it, it is still an uphill fight to convince anyone to do something that they didn't already conceive of before. You can show someone a vision of like, the 22nd century, and they'll just kind of look at it like the robots in Westworld looking at a picture of the outside world, and they'll be like, doesn't look like anything to me. And you're like, this is the good shit, dude. What are you talking about? And that, if I had a universal way to crack that, we would have to screen this from my yacht. But I think that's just kind of the human condition.
Absolutely. Thank you.
From watching your talk, you talk a lot about tools that are developed with more logical manual effort rather than with AI. But in 2025, everything is about AI. And you make the point that the work we do is inherently reactive. It's intrinsically tied to novelty and idiosyncrasy introduced by developers and other technologists. And large language models, things like that, are inherently based on what has been done. That's what they've been trained on, and they extrapolate from there. How do you think the reactive nature of the work we do affects the applicability of things like large language models to tool development here?
Yeah, so I do think that like an advantage that ML approaches have is that since the data either exists or can exist, you can do training. And so if you're saying, like, hey, I want to reverse engineer something, the source code for it or something similar to it has probably been seen by the LLM before. So I think this is a case where applying methodology, not wholesale, but those techniques can work in a way that might not work for doing wholly new idea generation, right? So like asking an LLM for strategy in some abstract domain, in my experience, hasn't worked out super well because there's a lot of like, hey, I've never seen anything like this before. Can you come up with something? And since mostly what it's doing is navigating this extraordinarily high dimensional space of things and concepts that we learn from the internet, if that isn't in the map, it's just gonna like make a whole bunch of stuff up. But if it's close to like, hey, yeah, here's like here are these concepts, can you navigate it for me and give me something that is like what you've seen before, it'll probably work better. And I think that definitely one thing, like one place that I was very excited to see, this is before the LLM and like tensor and attention architecture phase, but people were working on using ML approaches to do variable and parameter naming and decompilation output. And that seemed like a pretty decent fit. You would say, like, I've seen millions of different function bodies where the functions have good names and the parameters and variables have good names. Here's decompiler output. It looks kind of like some of the stuff I've seen before, and parameters and variables are used in like similar ways, so we'll give them the same names that they had in the other thing, and then things get named count and index and array the way that they did in the other one, where we had labels. That seemed to work like pretty well, and we could probably keep doing more of that because you have the data and you can do the learning. So I think, yeah, being able to be reactive is an advantage in that particular case because you have a large amount of data to draw on.
Hey, I'm over here. Hey, I didn't quite catch your definition of longitudinal understanding. Would you repeat that?
Yeah, so this would be something like, I'm always interested, like hypothetically, in the security properties of Linux kernel. Linux kernel is a bad example for reverse engineering because it's open source, but it's like, yeah, as things are, like I just want to like understand what's going on in that code base or like Chrome forever. I'm never going to not be interested in it. So what are the different security impacts or like functional understanding impacts of different chunks, like different subsystems, like the allocator, memory transfer things? As changes happen there, how does that factor into previous understanding that we've had? The longitudinal aspect comes from like we're going to consider that for years or decades. And this, yeah, does that make sense? Cool.
All right, for any other questions, go ahead and find Andrew outside or during one of the meals or the breaks. Again, thank you very much.
Thank you.